All right, everyone, we're back, and we're going to do now root locus with a slightly more complex system. So suppose we have this plant function, still have our controller, so our L of S would be defined, written in that essentially form. So our characteristic equation will look like this, and we actually have basically a system like here and like so. And we can start to look at what the poles are. So I always like to set this up in Mathematica. So this is our C of S, our G of S transfer function model. Remember, I would suggest just take this out, put it here, and let's start to simplify. So I would take this full simplify, and I would just say G as simple. Let's define that here. And now you can say G as simple. And we know, and we can actually go ahead and say, what's the transfer function poles for transfer function model G as simple in terms of S. And we have two poles, makes sense. So everything's looking okay. So let's go ahead and let's see how this looks as we increase. And actually, we can kind of see. So right now, if we look at the system, before we even get it, we're complex poles. Basically, we're stable here. And as we increase K, oops, what don't you like here? What doesn't it like? Transfer function model here, we need to put S. I don't know why that's... Suddenly doesn't like it, probably because I had already set it up there. So we increase. So if we just set our value here, for example, 0.5, we have our complex poles, and as we increase, at some point, at some particular value, we're increasing along that plane. Oops. Oh, we can have it play. We're just increasing on that y-axis, right? Except there's some special thing that happens at 10. No, it's just like so. So we can kind of see and observe essentially the motion of those poles, right? And essentially where they're going as we increase. So if we're less than 1.4, we're real and distinct. Once we get to K equals 0.4 and greater than 0.4, they become the complex conjugate. So actually we can see at the very beginning, let's go ahead and look at this. So let's go ahead and say 0.2, real. 0.1, real. But once we get to 0.25, there. Once we get just beyond that, complex conjugate. So we're still stable, right? Our system is stable and real at this point. Once we get to 2.6 or 0.6 or past 0.26, now we're getting at the point where they're complex conjugates, and we can now see we're going to have some oscillations in that system, right? Instead of just that exponential decay. So that's essentially how those poles are moving. And remember, we see that this real part stays here, imaginary part grows as you go to infinity. So that's kind of where the pole motion occurs. Now let's plot that in our root locus. So that's our transfer function model, and we can look at the root locus plot, and you can kind of see the motion of those poles, right? We're initially real, right? So let's break it, or let's kind of come back here, because I think it's always very helpful to kind of see this and visualize. We just visualized it, but let's look at the numbers here. So if I take this out, I'm going to just take this whole thing out. I'm going to take this, I'm going to say slash dot K goes to 0. So we're sitting initially at -2, -1, everything makes sense. As we start to increase 0.1, we see that those values start to move in. This is the location, right? As K is increasing, the -2 goes in, the -1 starts to get bigger over here, and at that magic number of 0.25, they converge at -1.5, and then after that, as we increase further, 0.3, now they start to move up and down respectively, and you can see right here where and how those poles move, like which one goes up, which one goes down. So it's a really nice way for you to visualize and see where are those poles moving. So it's a really cool technique, very, very, very helpful. These are not correct, and I'll have to update those later, but you can kind of see what we just did in this video to really visualize and see how that system is behaving. What is that transfer function, really looking like, even if you're doing the L of S, but also kind of making sure that they're all connecting. So fantastic. Let's see if we have this poorly designed system. So here we know we're going to have a 0 in the, basically, we're going to have a zero in the right half plane, and poles at this. So this is not necessarily a great system whatsoever. So let's go ahead and let's break this one down. So let's go ahead. We have our C of S, our G of S. We want to simplify this again. We want to do this and this. I'm going to do full simplify. And I want to say my G of S, GS simple is equal to here, GS simple, and then have a function of S. And let's see how this system is behaving here. And I want to look at the, again, transfer function poles with transfer function model of GS simple S. So second order system again, and we have exactly second order system again, and now we can kind of see, again, real initially, right? So if we put in a value of, let's just do 0.1. We're initially real. We have that 0 in the right half plane, and we see as we increase, we can actually push one of our poles into that right half plane. So we could actually make our system unstable. That's not good. And that's what the poles do, right? The poles attract, they pull, or the zeros, will pull. If you have a controller, it could pull essentially a pole into the right half plane. So we don't want to have zeros in that right half plane. So as we're increasing the controller, there becomes a point where we can now destabilize the system. And mathematically, we can essentially see as this goes to infinity, constant upper curve will eventually become negative, and then become unstable. So for k greater than 2, and we can actually, let's prove that. Exactly, right here. So once we're greater than 2, it's over. So that is very, very not good. That's not good at all. We can increase that k. This is kind of for the other systems. We can destabilize the system, and we can look at it on the root locus as well. The root locus, I really like to kind of visualize this here. So again, kind of same idea, right? Even as you're increasing, this one is going to minus infinity, but this one now is starting to basically go into that right half plane. So you can see everything was looking all good. 1.5. Everything looks nice here, but you kind of start to see it creeping over, and then by the time you hit, 40, you're really starting to see this one's going to infinity, but now it's going to basically move and then eventually hit and terminate at that 0. So you see how your poles are moving around in this system. So that's the kind of the power of root locus. We can understand, we can visualize how this graphically, how this is going to look like. And so that's really, really cool to kind of see. And you see the distinct pole motions, and you can track it to your K, and essentially see the continuous, paths of that, of how the poles will move. Now, it's great because we can predict how they're going to move. We can see, are we in a dangerous spot where we're pushing the system into an unstable region? Just by looking at essentially our transfer functions and the plants, and rewriting in that system. And there's certain rules that are fundamental to essentially to root locus. Now, you see here, you're going to we're going to just generate the plot automatically with Mathematica. But it's really, really helpful and fundamental to kind of understand the rules and to kind of see how these plots are generated. And then you can gain some insight into that physical system. And that's really, really important. So we're going to go over essentially all the rules for root locus. This was really typically to draw your own, but you can kind of imagine, use this and leverage these techniques and leverage this insight into designing your own control system. So we'll see you all next time. Thanks.